Hi, in this lesson we are going over a few examples on how to graph a rational function. A rational function is the function that has the ratio between a polynomial and another polynomial. In this case, we are given this rational function and we are asked to find the domain, the intercepts x and y, the holes, asymptotes, and also the side of the graph for this function. So before we find any domain, x, y, intercept, or any hole, any asymptotes, the best way for any rational function is that we have to rewrite them in the factor form on the numerator and then denominator. On the top here, we can see that we can pull out a 10, the common factor, because 80 and 10, they have a common factor of 10. So I can take 10 to the front, and then when I take 10, I have only x left here. When I take 10 out, I have 80 divided by 10 is 8 here. For the bottom fraction here, we can factor by using the grouping. So I can group the first two and also the last two terms together. Between the first two terms here, I see I can pull out the x squared. When I take out the x squared, I have x left here, and I have minus 4 for the second term. For the last two terms, I see 16 and 64. I can pull out 4. So we can do that. I can, but there's a minus here, so let's just take out the minus 4. So if I take out the minus 4, I have plus 4x left for the first term. Actually, between 16 and 64, we can just take out 16, right? Minus 16, because 16 divided 64 divided by 16 is 4. So let's do that. Okay, so we can take out a 16 minus 16. When I take out the minus 16 here, I have x left for the first term, and then 64 divided by minus 16, we have minus 4 left for the second term. And we can see one more time that there is a common factor of x minus 4. So I can take this one to the outside one more time. When I take x minus 4 to the front, I have x squared left for the first term. And then I take out x minus 4, I have minus 16 left for the second terms. Okay, but we see that x squared minus 16, this is the difference of the square, or x squared minus 4 squared. And using the formula, you can see we can write that at x minus 4 times x plus 4. So x minus 4 times x plus 4, but we already have x minus 4. Therefore, we have x minus 4 to the second power multiplied by x plus 4 here. So this is the factor forms for this rational function. Now, once we get the factor form, it's easy to find the domain. Remember, the domain of the rational function can be all real numbers except the point that makes the denominator to become 0. So we don't want the points, the values that make the denominator to become 0. Therefore, I take the denominator here, I set it equal to 0. And once we set that equal to 0, we need to solve for the value of x that make that to become 0. And then we exclude those values outside of your domain. Now, x plus 4 times x minus 4 squared equal to 0. That means either this one, x plus 4 equal to 0, or x minus 4 squared equal to 0. There are two cases, right? X plus 4 equal to 0, that means x equal to minus 4, just solve for x. Or x minus 4 equal to 0, that means x has to be equal to 4. So these two values, minus 4 and 4, are the ones that make the denominator to become 0. And that's why we do not want these two values, and we exclude them outside of the domain. So we go from negative infinity up to minus 4, not including 4. That's why we are using the open parentheses. And then union with minus 4 up to 4, and then from 4 all the way to infinity. So that is how you find the domain of this rational function. Now for the intercepts, there are two types of intercepts, x and y. How do I find the x-intercept? In order to find the x-intercept, you let y or the function to be 0, and then you solve for x. But if I let this whole thing here to become 0, and then solve for x, and just to pay attention here, the denominator cannot be 0. So the only way that can make the function to become 0 is that the numerator to become 0. That's why when I solve for x-intercept, I let the function to become 0, and the only way that it can be 0 is the numerator to become 0, because the denominator cannot be 0. So we set 10x minus 80 to become 0, which means x minus 8 equal to 0, or plus a on both sides, you get x to be 8. So x is 8 and y is 0. This is the x-intercept. And for the y-intercept, we do the opposite. We let x to be 0. So I go ahead and substitute x to be 0 to here, and also here, here, and here. And after doing some calculations, I end up with minus 5 over 4. So minus 5 over 4 is the y coordinates, and 0 is for x, because we are solving for the y-intercept. So 0 should be x. So after we have x and y-intercept, we are looking for the hole. In this case, we don't have any hole. From section 5.2, we know that if we have a common factor on the top and the bottom, when we cancel that out, then that factor will make the hole in the graph. But in this case, we did not cancel anything, so there are no hole in this case. And now we can find the critical numbers. The critical numbers are the one that we are using that to help us to graph the function. So let's try. What should be the critical numbers? The critical numbers are the number that make the numerator or 10x minus 8 to be 0, or the denominator d of x to be 0. So we are solving for the case when the numerator is 0 or the denominator to become 0, and those values that makes the top and the bottom to be 0 are the critical numbers. So when we have the numerator to become 0, we already did that here, right here, which is the value which is 8. So that should be 8 here for x. And when the denominator to become 0, we also found it here, which is minus 4 and 4. So we write up down here, minus 4, 4, and 8 are the three numbers of x that make the numerator and then denominator to become 0. And these three values are the critical numbers. So we plot them on the number-line system. And then now we know that minus 4, 4, and 8 will divide the graph into 1, 2, 3, 4 different regions. And now we can do some testing to find the side. So on the left side of minus 4, I just take one random number, maybe minus 5, and then take minus 5. I substitute that in here. I see that the whole function gives me some positive value, which is plus. And then between minus 4 and 4, maybe I pick 0, and then I substitute 0 in here for x, and my original function tells me that it should be a negative value. And then between 4 and 8, maybe pick x to be 5 and then substitute that in for x, and I get some negative value. And do the same thing to the right side of 8. I guess a positive value. So getting the size of the graph will help me to later on to graph the function, and we will see that shortly. Now after we get the domain, the x-intercept, the y-intercept, the whole, the size, now it's time for the vertical asymptotes, horizontal or oblique, or the slant asymptotes. For the vertical asymptotes, remember the vertical asymptotes, to find the vertical asymptotes, we set the denominator to become 0 and we solve for x. And the denominator in this case is this one, which we already solved for the case when it's equal to 0. So x equal minus 4 and 4. Just write it down here again. And for horizontal asymptotes, there are 3 cases. The first one, if the degree on the bottom is bigger than on the top, then the horizontal asymptotes y equals 0. If the degree on the top is bigger than the bottom, then there's no horizontal asymptotes. If the degree on the top and the bottom are equal, we take the ratio between them. In this case, the degree on the denominator is 3 and the numerator is 1. Therefore, the bottom part is bigger, and we have 0 as the horizontal asymptotes, or y equals 0. This is the rule from the last section 5.2. Now for the slant asymptotes, we only find the slant asymptotes if the degree on the numerator is bigger than the degree in the denominator. But in this case, it's not bigger than the denominator, therefore there's no slant asymptotes. If it's bigger than the bottom fraction, I mean if the degree of the numerator is bigger than the denominator, then we can use the long divisions to find the slant asymptotes as in the last section. But in this case, it's not, so we don't have any. None. Okay, so now we have every information that is required, and now it's time for us to plot the function. So in order to plot a function, is the best way to first plot the vertical asymptotes. So we know that x equal minus 4 and x equal 4 is are the vertical asymptotes. So I go ahead and plot them. This is minus 4. So plot the vertical asymptotes. And then plus 4, which is here. What about the horizontal asymptote? Is y equals 0. So it's just basically the x-axis, right? It's just the x-axis. And okay, so we have the horizontal and vertical asymptotes. Now let's plot the x-intercept 8, 0. So 8, 0 should be, okay, 5, 6, 7, 8, 0 is here. Yes, right here. Okay, and then the y-intercept is 0, minus 5 over 4. So minus 5 over 4 is around here. So we know that this is around here, right? So this is 8 and 0 is here. For x-intercept and y-intercept is 0 and minus 5 over 4. There's no hole. Okay, so now we can start to graph the function. Okay, so if you want to graph the function, we have to go back to the critical numbers here. So before the minus 4 on the left side, minus 4, the graph should be positive. That means it should be above the x-axis, right? And the only way it can be that is by, we know that as we moving to the right side, the graph has to be approaching the x-axis because this is horizontal asymptotes. And as we move to the right, eventually it must approaching to the vertical asymptotes and never cross those two vertical asymptotes. So we know that the graph has to be this way, because as you go to the right, it's approaching the vertical asymptotes. As you go to the left, it's approaching to the horizontal asymptotes. And it is in the positive region because of the side here. And now between -4 and 4 must be a negative value. So -4 and 4 here, it should be down here. It should be down here. And we know that the function, as we move to the left and to the right, the function must approaching to the vertical asymptote here, right? It's must approaching the vertical asymptotes here, and it's moving down because of the negative value between -4 and 4. And we know that there's a y-intercept here, therefore it must connect to that y-intercept, and then it's moving down here. Okay, so it's must going up here and connect to the y-intercept, and it's must going down on two sides in order to approach the vertical asymptotes on the right and the left side. We cannot go up because we don't want the positive value. It must be negative value. So it must going down this case in order to approach the vertical asymptotes and also cross to this point for the y-intercept. And then the last one, the right side of between 4 and 8. Okay, so between 4, which is here, and 8 is here. Between 4 and 8, we know that the graph has to approaching, it has to be negative between 4 and 8. It has to be negative between 4 and 8. Right here, 4 and 8 is negative, therefore it's must going this way until you hit 8. Because you cannot show anything above here, it must be negative. And because there's vertical asymptote, it's approaching the vertical asymptotes and also the horizontal asymptotes here, and then crossing the 8. Now, after you hit the 8 for the x-intercept 0, 8, 0, then from 8 to above the right side of 8, it must be positive value. So from here and then beyond, it's just going up because it's positive now. Right, it's just going up, positive now. And that should be the graph of this function. Once we figure out the horizontal asymptotes and the vertical asymptotes and the y-intercept, x-intercept, then it's very easy to follow the graph, the vertical asymptotes, and the side of the graph to draw the function. Okay, let's move on to the next example, another example. So again, the first thing is we have to factor the numerator and the bottom part here in the factor form. So we can do this by grouping. Again, I can group the first two terms together and the last two terms. Now you can see that I can pull out x squared for between the first two terms, and I have x left and -2. And then for between the last two terms, I can pull out the minus sign, so I can have x as the first one, and I take the minus side, so I should have -2 for the last term. And then I can see we have the x -2 as the common factor, so I can take that away. I mean, sorry, x -2 to the front again, and now I have x squared left and then -1. Let me write this one. Okay, should be 2 here. And x squared -1 is the difference of the square. So that becomes x -1, x +1. So we can see that x minus 2 times x minus 1 times x plus 1, right here, these three. And then the bottom parts, we can factor this trinomial, three terms, into x and x squared, and minus 1 and minus 3, because minus 1 times minus 3 is plus 3, minus 1 minus 3 is minus 4, the midterm here. Now we can see from here they have the x minus 1 as the common factor. I can take that away, x minus 1. So I have x plus 1 times x minus 2 over x minus 3. And don't forget that if you cancel the two factors, this will create a whole where x equal 1 is the whole. Because 1, if you plug in 1 here, 1 minus 1 is 0. That makes your denominator to become 0. So if you can, even if you cancel that, we still have the whole at that point. The last example, we did not cancel anything. So now let's find the domain. The domain again is we set the numerator to become 0, but we take the final expression here, and x minus 1. Sorry, the domain is of any rational function is every real numbers except the point that make the denominator to become 0. So we set the denominator here to be 0, because x equal 1 is 0 for this term. So we take these two, even though we cancel out these two guys here, but it will still make the domain to become 0 as the whole. So we set x minus 1 times x plus 3 to become 0, and then we solve for that, which is x equal 1 or x equal 3. So we exclude that outside your domain, which is these things. And then for the x-intercept, again, for the x-intercept, we let y or t of x to be 0, and then solve for x. And the only way that make t of x to be 0 is the numerator to become 0. We don't want the denominator to become 0 because that will be undefined. So that's why we only set the top to be 0. And the top is these two expression to be 0, because we take the final expression after we cancel out the term. So x plus 1, x minus 2 to be 0. That's give me x equal minus 1 or x equal 2. And these two are the x-intercept. For the y-intercept, we let x to be 0. So I substitute x to be 0 to here. Sorry, to here. So 0 here, 0 here, 0 here. I get 2 over 3, or 0, 2 over 3 is the y-intercept. And the whole happens when x is equal to 1, as I mentioned here. And in order to find the whole, we take x to be 1, and we substitute that back in the final expression, 1 here, and 1 here, and 1 here, and find what should be the y value is also 1. So 1, 1 is the whole. Now, to find the critical numbers, we take the points, the value that make the numerator to become 0, and also the denominator to become 0. And we know is from here, this is the denominator to become 0 when x equal to 1 and 3. So we have 1 and 3. And also when the numerator to become 0, so that is minus 1 and 2. So minus 1 and 2 here. The reason that I did not include the minus 1 for here, because that is already the sorry, the reason that I did not include x to be 1 as the critical number, because that is already the whole. Okay, it's here. Okay, so again, I pick some points and test for the sign minus plus, and that will help us to graph the function. Now for the vertical asymptotes, we set the bottom, the denominator to become 0. So that happens only when this thing to be 0, or when x is equal to 3, which is here. And horizontal, we go back and we check. We see that in this case, the horizontal, we don't have any horizontal asymptotes because the degree on the numerator is 3 is bigger than the degree as the denominator, which is none. So if the top is less than the bottom as in the last case, then that's equal to 0. If the top and the bottom they have the same, we take the ratio. If the top now is bigger than the bottom, then there's none. There's no horizontal asymptotes. And the last one, we also see that the degree in the numerator is also bigger than the denominator, and therefore we can find the Slant asymptotes by using the long division. Okay, so we can do the long division here. Let's try that and see what we get. Okay, we can do the long division in a separate paper here. So in order to find the long division, we take x3. The first thing is we know that this is written in the descending power 3, 2, 1, and 0. Okay, also 2, 1, and 0. So we can take x3 divided by x2, that give me x, and multiply x to x squared, that's x3, x to 4 minus 4x squared, x to 3, that is 3x, and then do the subtraction, that is gone, 0, minus 2 minus 4, that becomes plus 4, so plus 4x squared minus 2x squared is 2x squared plus 2x squared, and minus 1 minus 3x, that is minus 4x. And now we take 2x squared divided by x squared, that gives me plus 2, and so multiply 2 to here, and don't forget to bring down the next term, plus 2 here, and then 2 times minus 4, that's minus 8x, 2 times 3, that is plus 6, and then now subtract that, I get 0 for here, minus 4 minus become plus 8, that become 4x, 2 minus 6 is minus 4. Okay, so from here we are no longer be able to divide 4x to x squared, so this is the remainder. So the way we write the answer is that we write the result x plus 2, and we add to the remainder 4x minus 4 over the denominator here, x squared minus 4x plus 3 for the long division. And the Slant asymptote is just the result that we get here, or x plus 2. So go back to the question here, we know that the Slant asymptote should be y equal x plus 2. And now let's go ahead and graph this one on the function on the xy plane. Now the vertical asymptote is x equal 3, so I go ahead and draw the vertical line as x equal 3, which is right here, x equal 3. Okay, let me take away the noise here. Okay, and we don't have the horizontal asymptotes, but we have the Slant asymptotes, that's y x plus 2, that is the linear. So 2 is here, so we go up, the slope is 1, so which is around here, and we can draw the line. This is y equal 2, and this is the Slant asymptote. Okay, and then now the next thing is we have to plot the whole. The whole happens when x equal 1, y equal 1, so which is right here. The whole is here. X-intercept is minus 1, 0, which is here, and also 2 zeros here. Y-intercept 0 and 2 thirds, so 0 and 2 thirds, which is around here. Okay, so we can graph the function now. We know that the lines have to be approaching these two asymptotes here, and we know that it must go to this point here, So it's just approaching the line here, and also it's going down here again, approaching here, because between 2 and 3. Okay, let's go back to the critical number. Anything after -1, which is here, it has to be negative, so we are correct here. Between -1 and 2, it must be positive region, and then after 2 to 3, it has to be in negative region, so it should be going down here. And then after 3, above 3, it must be plus, so after 3 here, it should be around the plus side, and we know that it must be approaching these two asymptotes. So the only way for that to happen is we have to judge this way, because it must be between these two asymptotes. We cannot judge here, right? Because if we judge here, it's we're going down, and we don't want the negative value, we want positive value, so it must be up here. Okay. So as long as we get the asymptotes, the whole, the x, y intercept, then we can graph the function easily. Okay, let's see the last example. We are finding a rational function. We are looking for the function, the equation that might have the given graph here. Okay, this is a little bit easier than the last two examples. The first thing is we are looking for the horizontal asymptotes. In this case, we do have the vertical asymptotes as y equal 3. So we know that the degree of the numerator and denominator has to be 3, because that is equal to the horizontal asymptotes. And 3 is 3 over 1, or the coefficient of the numerator has to be 3, the degree has to be 3, and the degree of the coefficient of the denominator has to be 1. So 3 over 1. This is the info we got from here. And we also know that the vertical asymptote has to be at 5 and -3. Right? So 5 and -3, vertical asymptotes. So if it has -3, then the factor must be x plus 3, because x plus 3 equal to 0, then x should be -3. And x equal 5, another vertical asymptote here, or x has to be x minus 5 to be the factor, because x minus 5 to be 0, then you solve for x to be 5. Now we also know the x-intercept, which is here around -2 and 0 here, so it must cross through the point x plus 2, because x plus 2 equal to 0, then x equal -2, right? So we factor the numerator to be x plus 2, because the x-intercept is the one that makes the function to be 0, or we set the numerator to be 0, and this thing set to be 0, we will get to -2. And we also know that we also have one more x-intercept here, but it's touching, it's not crossing, it's just touching as 1. So we have another 1, 0, or x minus 1, because x minus 1 to be 0, so x equal 1. Because it's crossing, we have the odd power or the first power, and the touching, we have the even power or the second degree, the least even power. So we have these two as the factor of the numerator. So I have x plus 2 and x minus 3, x minus 1 square. So this comes to the numerator for the x-intercept. And for the denominator here, I have x to be -3 and x 5, and these two are the factor. And we go back to here, we know that as x equal -3, the two graph is going in the opposite direction. one go up, one go down, approaching this line. Therefore, it must be the odd multiplicity, or it's the one here, the least odd power. And for x to be 5 is here. We see that the two graphs is they are approaching with the same direction, so that must be even power. This rule comes from the last section. Therefore, it's the least even power 2. So these two here go to the bottom parts. And we know that the degree, the ratio must be 3 to get the horizontal asymptote to be 3. Therefore, I must put a 3 here on the top, so that is equal to 3 here for the horizontal asymptotes. So this is one of the possible functions that could represent for this whole graph here. All right, we'll do more example in the class next week, and thanks for watching. So that should be the end. Yeah, and this is just a quick summary for the thing we just do so far in the class, in this section.